Hi, welcome back to the part 2 discussion on DH parameter selection. In the previous segment, we talked about some very basic concepts of DH key exchange, and I explained how the DH algorithm actually works. We talked about what is a cyclic group and what is a generator, and why do we need a prime to generate the keys in a way that it's not easy for an attacker to easily brute force. Today I'm going to talk about the next part, which is why do we need a safe prime when we use DH. Traditionally, DH algorithm works without a safe prime, but in recent years rather, safe prime is actually used in TLS and SSH and other protocols. So I'm going to talk about the safe prime usage in this part of the video. Okay. So we have been playing with this little DH generator program, which helped us to understand the importance of this prime P and choosing the correct G so that we get all the elements of the group generated. There is one fundamental theorem I would like to explain to you today, is that let's try with our simple prime P equal to 13, G equal to 2. We do know that there are 12 elements in that group, multiplicative group. So I'll put it 12. Let's run this with this configuration. We can see that G equal to 2 actually generates the entire group. You know, if you count, you will see 3, 6, 9, 12 elements. There are 12 elements in ZP star, which is in this case 13. So P is 13. That means there are 12 elements in the group. Okay, the order of the group is 12 in this case. Okay, order of the group is 12. Order of the group is 12. Is 12 because P is equal to 13. Okay, just want that to be clear. However, there is an interesting theorem now. What happens if I change the G? Let's say I change the G to be 3. What is the order of the subgroup? The order of the subgroup is just 3. Okay, order of the subgroup is 3. Okay, it turned out that let me try one more configuration. Okay, let's try G equal to 4. I haven't checked what order of this group subgroup is 6. Okay, so it turned out that the order of the subgroup, the theorem is this. Theorem is order of the subgroup divides the order of the group. Okay, this is an interesting theorem. Lagrange discovered this theorem. We need this theorem for our Diffie-Hellman key exchange. Actually, when we talk about these, the reason why we go for the safe prime, we will leverage this theorem. So in our example, the subgroup, we started with the group of order 12, right? That's 12 elements. When P is 13, we have 12 elements. So order of this group is 12. What are the divisors of 12? 1, 2, 3, 4, 6, right? And 12. So there must be 6 subgroups for this, because 12 is divided by 1, 2, 3, 4, 6, and 12, right? So all of these subgroups are generated by different G's. If you play with the different G's like the way we did, we can generate all of these subgroups. Okay, this is a fundamental theorem we need, Lagrange's theorem. What is the reason we need now safe prime? Okay, well, let me get this theorem out of our way. We understood this. If you recall now, when I played with my G, depending on the G, I get different subgroups, right? In this case, for example, I get the full. Let me change my G. Okay, G to be say 3. I get only subgroup of order 3 because after 3 it repeats. Okay, what it means from a security point of view is that if G is not properly chosen, what will happen is that the number of possible keys is actually really small. Remember, the way DH key exchange works is this G actually generates a group, right? If the group is only small, then the keys must be in that small subgroup, because this is how we get the key in the first place, right? The key exchange algorithm we talked about in the previous part. I will quickly show you what I mean by that. Okay, here it is. Alice picks a number X, Bob picks a number Y. These are private numbers. Alice computes G power X and sends A to Bob, and Bob does G power Y and computes that and sends that to Alice. And then Alice takes Bob's public key and writes it to her private key X, and she gets the same key K because of exponential properties, right? Exponent properties rather. So both Alice and Bob arrive at the same key K. Okay. So if G is small, you can imagine the possible values for A and the possible values for B will be small. Meaning, when I say small, if G only generates a small set, since A and B are an elements of a small set, the element K, the secret element K, will also be an element of a small set, because K itself is actually indirectly derived from G, right? If you replace A by, what can we replace A by? A by G power X. So G decides the size of the set, and if the size is large, it will be difficult for Eve to figure out the key K. If the size is small, then she immediately can find out the key K. Okay, so that's the reason why we need a good generator. Okay, the G is the important part. All right, so if G is not carefully chosen, or somebody tricks you to choose a small G, in the sense that the G doesn't generate all the elements of the group, your key size is very limited, in the sense that the number of key possible values will be limited. Okay, the key can still be large from an external point of view, but the key is actually coming from a really small subgroup. That's not good. Okay, all right, that's the reason why we need a good G. But then how do we check whether the G is good or not? Suppose somebody say the government is generating a P and G for us, which is often the case. How do we know that G itself is not a backdoor G? Like if G is only generating a small subset, then you can easily find out all possible keys very quickly. Okay, so for that we need a safe prime, and safe prime is interesting in the sense that, so let me define what a safe prime is first. A safe prime allows us to do computations in a relatively safer way. So what is a safe prime, by the way? So a safe prime has some structure like this. Q is also prime. P and Q are both primes. Okay, but P must be equal to 2 times Q plus 1. Okay, this kind of primes is also called actually Sophie Germain primes or something like that. She's a French mathematician. So anyway, something similar. So this is basically the safe prime structure. Okay, why do we need safe prime in DH algorithm? The reason why we preferred safe prime is that, now think about the order of this group. Okay, remember the order of the group is basically P minus 1, right? If P was 13, order of group was 12. What happens in this case? The order of the group ZP star is nothing but P minus 1, which is nothing but 2Q. Okay, so what are the divisors of 2Q? So we will have subgroups. What are the possible subgroups? Possible subgroups are 1 are of size 1, order of the subgroups. Okay, 1 divides 2Q, 2 divides 2Q, Q divides 2Q, and then of course 2Q divides 2Q. There are only 4 subgroups. Okay, and who can generate the subgroup of order 1? Well, only if the generator G is 1, then we will have the subgroup of order 1, subgroup of order 1. So we can easily eliminate. If somebody sends us a G to be 1, we say, well, this is not good, we will eliminate. Okay, what about subgroup of order 2? There are only actually 2 possibilities, right? That means the generator is like this. If this is the generator, generator G is basically P minus 1. If G is equal to P minus 1, it will generate a subgroup like this. It will generate a subgroup 1 comma P minus 1. Okay, so we do quickly recognize that these 2 are not good subgroups because there are only 2 possible keys, right? So we can eliminate essentially G equal to 1 and G equal to P minus 1 very quickly. And now we know that the remaining groups are actually either a group of order Q or a group of order 2Q. Okay. How do we now check whether we have an element that generates a group of order Q? Remember, Q itself is a prime. Okay, so we need how can we get a G which will only generate a group of order Q, not necessarily order of 2Q. Okay, one simple trick we can do is we select a random element, say alpha, right, and then we compute the alpha square. Okay, if we compute the alpha square, this is not exponent symbol, this is alpha square. Okay, this actually is good. If G is not equal to 1 or P minus 1, okay, or not equal to P minus 1, we are good. This G is good. This G will generate this G. What is alpha, by the way? Alpha is just a random element. Alpha is a random group element. You can just randomly select a group element from ZP star. That's not a big problem. It's easy to randomly pick an element and check whether it's a member of a group. Okay, a polynomial time algorithm will do that. And now this G actually will generate a subgroup of order Q. Okay, that's all. So we got a good G which will generate a subgroup of order Q. Why is this so exciting? What is Q? Q itself is a prime number. Therefore, there cannot be any subgroups within that group. Okay. The important fact is that since 2 is prime, okay, no number will divide a prime number other than 1, of course. Therefore, that it cannot have any subgroup, right? So what it means is that Q, okay, G will have to generate the entire subgroup of order Q only. There cannot be any subgroup attack. Okay, meaning you can't select a G that will only generate a small number of possible keys. Okay, that is impossible, mathematically impossible. This is because of this theorem that we talked about. The order of the subgroup divides the order of the group. Okay, and if the order of the group is prime, you cannot find subgroups. Okay, that's basically it. Non-trivial subgroups. Trivial means 1. Okay, non-trivial is other than 1 and P minus 1. You cannot find any other subgroups. Okay, that's the reason why we prefer safe prime, because it's easy to check whether a generator actually generates. All we have to do is take the generator G, right? Check whether it is not equal to 1. Check whether if it is equal to 1 or equal to P minus 1. If one of this is true, we reject it. We say this is a bad generator. Otherwise, we accept all generators. We can also check G power Q is 1. Okay, why do we say that? We say that because what is G? G is some alpha power 2, right? Okay, and then we raise that to power Q. Now, if you do the math, what is alpha? Alpha is just a random number. We don't know what it is. How can we rewrite this thing? Very simple. What is 2? 2 is actually P minus 1 by Q from this equation, right? So we can write it as alpha power. Now it's getting a little complicated. B minus 1 by Q, right? The whole thing is in exponent, and again another exponent. Therefore, the Q and Q will cancel out. So we will end up with something like this: alpha power P minus 1, which is simply 1 because of Fermat's theorem. Okay, Fermat's theorem. That's all. So these are the important checks we need to do. If we get a generator from somebody else, we can check whether it's 1 or P minus 1. If one of this is true, then we reject it. Otherwise, we just take the G and raise it to power Q. Of course, we need to first make sure P and Q are primes, and we also have to make sure P is equal to Q plus 1. And then we check this. We just check this actually. And if this is violated, we know we are getting a wrong generator. Okay, so that's basically the math behind it. A lot of math. Very quickly, we summarized it. Now let's get into some experiments, and then I want to show you how this is implemented in real world with examples from the standard. Okay, that's what I'm going to do now. Okay, so let me get this thing out of our way. We have gotten all the math in place. I wanted to show you how the real world P and G and Q are generated, right? This is one of the TLS standards RFC 7919 for Diffie-Hellman groups. So you may read the details online, but I'm going to just show you the document contains an appendix which has some formulas formulae for generating the prime P. So let's consider this. If you want to say a 2048-bit Diffie-Hellman group, all we need to do is just copy and paste this P which they generated for us and this G, okay? And they also gave us the Q. So I wrote this little program which takes this P, Q, and G and check all the things that we talked about, okay? Just for our education purpose, we did that. So let me show you that. So what I did is basically a program that takes the P, Q, J in this case is 2 because we're talking about safe prime with the, you can imagine J is 2, okay, for now. These are basically printing the length of each of the integers P, Q, J, G. Okay, here is the Diffie-Hellman protocol. Like the Alice part will, Alice, what is she going to do? She's just going to generate a random element from the subgroup. That's why she's picking Q dot bit length, right? And then she will construct a Diffie-Hellman object using the GP private key Alice, right? And she will take the private key and she will raise the G power private key, and that becomes her public key, right? G power X, for example, becomes Alice's private key, public key. Now the same thing, let's assume she's going to send P, Q, G from Alice to Bob, okay? So we assume Alice is basically like a server, if you want to treat that way. She's going to send this to Bob. So what will Bob do? Bob has to check whether the prime that he got from Alice is actually a prime. So we will use Java's big integer is probable prime to check is it prime with certainty of 95 confidence level, if you want to call that way. I put 95 as a hard-coded constant somewhere here. Yeah, so you can play with it. So you check whether it's prime, P is prime, Q is prime, and you also check whether P equal to 2Q plus 1. That's what basically this expression is. And then you also check whether G is not equal to 1. If G is equal to 1, that's really bad. And you also check whether G is equal to B minus 1, P minus 1. If it is true, then it's also bad. We also want to make sure that G power Q is 1 because we want to make sure we are working with subgroup of order Q, right? That's all I explained it on my notes earlier. Okay. So after he checked all of those, he goes back to the Diffie-Hellman protocol now. He also generates a random number from the subgroup of order Q. That's the reason he does this. And then he basically computes his public key. Okay, so he computes his public key. Okay, what are they now doing now? Both Bob and Alice will have to check whether they exchange the public key, of course, and then they have to check whether this public key is coming from an element of order Q, because we want to only work with subgroup of order Q. That's simple. Public key of Alice is raised to the power Q mod P. If it is not equal to 1, something is wrong. Of course, we wanted to eliminate the simple ones like public key being the value 1, public key being less than or equal to 1, in fact, and the public key greater than or equal to P, because we can't have any element more than P. We have a group size at most P elements, right? Okay. Actually, we can only have 1 to P minus 1 anyways. Okay. The same thing Alice will do. So I will not explain that. Once both of them have actually confirmed this, they have to do it locally and check whether the parameters are fine. The next thing is just they mix up each of the public key with their own private key, right? So for example, Bob will take his private key and mix with Alice's public key. And the same thing with Alice. Alice takes her private key and mix with Bob's public key. So, and then we can assert that they both actually end up with the same data as I show on the slides. Okay. Usually in practice, we can't just use that session key directly. We need to apply some kind of a key derivation function, because this data that you are seeing here, it's a group element, not a uniform n-bit string. Okay, that's the reason. Okay, anyway, you can watch my other videos on HKDF to understand how that works, but that's not the main focus now. So this is basically the DH protocol. Okay, And I have actually implemented my own little DH protocol here. You have to feed in a G and a P and a private key. And then it's basically as simple as this. Generating a public key means take the G and apply the private key as power. G power private key will give you the public key and so on. Okay, so this is simple DH explained on the slides. All right, so let's just run this thing. What I did actually, copy and pasted the data from the standard and put it into my file here, you know, P, Q, J is 2, because we're talking about P equal to the primes of the form P equal to 2 times Q plus 1. That's the reason my J is 2. Okay, so I will just copy and paste this and show you how a session key can be established with these parameters, right? Let's copy this and let's try this. What we are doing now is we are generating the session key, shared session key, right? The shared secret key, if you want to call it that. So this is the shared secret both Alice and Bob have by doing Diffie-Hellman on the data that we got from the RFC standard. Okay. So if you wanted to mess with it a little bit, I have actually enabled the exception, so we can add it here, right? Let's see. What happens if I just put my G to be 1? Of course, now the shared secret won't come. Yeah, you don't see shared secret because I checked in my code. I didn't put an error message. Your G cannot be 1. Okay, that's the reason why we have this problem. Anyway, that's one quick demo of how the safe prime is used. The point to remember is that the safe prime helps us to systematically evaluate that the generator we are getting is a good generator. The generator indeed generates the entire subgroup of order Q. If somebody backdoors the generator, we can actually detect that it is not generating the entire subgroup. Okay, then generating the entire subgroup is important because we want to make sure that each and every group element can be a potential key. That's the reason why we need a good generator. Okay, so that's basically what I wanted to show you in this part of the demo. In the next part of the demo, I will show you a more generalized version of it because the RFC allows us actually to use something called short exponents. So the idea of a short exponent is pretty cool. Instead of working with P equal to 2Q plus 1, we would be working with group primes with the more structure inside. Will make the algorithm much faster. I'm going to show you the details in the next part of the demo. Thank you very much.